chapter 11. And the first section of that chapter, 11.1, is about the three-dimensional coordinate system. Our goals for today are that we can plot coordinates in three-dimensional space. We can find the distance and midpoint between 2 points in three-dimensional space. We can write equations of spheres and ellipsoids and find their volumes. Some definitions for you. The three-dimensional coordinate system has x, y, and z axes, where the z-axis is perpendicular to the xy plane through the origin. These create three coordinate planes: the xy plane, the xz plane, and the yz plane. And these planes separate the three-dimensional coordinate system into 8 octants. So with our two-dimensional coordinate system, we have the 4 quadrants. In the three-dimensional coordinate system, there's 8 octants, which look like this. Sorry. So in octant 1, all 3 of your coordinates are positive, x, y, and z. In quadrant 2, in octant 2, your x is negative, but your y and z are positive. The axes are labeled in the direction that's positive. Okay, so in octant 3, our x is negative, our y is negative, but our z is positive, and so on. It's not super important that you know this. We're not going to ask you to label which octant a point is in, but know that we can use this to better describe points within three-dimensional space. Sorry. All right. Example 1, plotting each point. I'm just doing this to show you what it looks like to plot points. We're not going to make you plot points on your own because it's really difficult to do unless you have some three-dimensional graph paper. Well, it's a three-dimensional axis on a two-dimensional graph, so it's still not perfect. It's a little bit distorted. But if we want to graph point A, -1, 3, 4, we would go to -1 in the x direction, then +3 in the y direction. So -1 in the x direction, +3 in the y direction, and then up 4 in the z direction, plot our point. The point 2, 5, 0, we would go to +2 in the x direction, +5, 5 in the y direction, and up nothing in the z direction, so there's our point. Point C, 1, 3, -2, so +1 in the x direction, 1, 2, 3 spaces in the positive y direction, and then down 2 spaces in the z direction. And you can see that if you're trying to do this, a lot of times it's helpful to draw in some extra lines to help you keep things straight. And our last point here, 2, -1, 3, so +2 in the x direction, -1 in the y direction, and then up 3 spaces in the z direction. And there's our point. All right, distance and midpoint formulas in space. The distance between the point x1, y1, z1 and x2, y2, z2 is given by distance equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared plus z2 minus z1 quantity squared. The midpoint of the segment joining those points is given by x1 plus x2 all over 2, y1 plus y2 all over 2, z1 plus z2 all over 2. Notice that these formulas are very similar to the distance and midpoint formulas for two-dimensional space. We've just added this third component with the z coordinates. But otherwise, the formulas function in the same way. All right. Example 2, and find the distance and midpoint between these 2 points. 2, -2, 4, and 1, 3, 6. So we have this one we'll use as our first point, so x1, y1, z1, and our second point here, x2, y2, z2. To find our distance, we're going to substitute into our distance formula. So if we put 1 in for x2, minus 2 in for x1, put in 3 for y2, and negative 2 for y1, put in the 6 for z2, and the 4 for z1. 1 minus 2 is negative 1. 3 minus negative 2 gives us positive 5. 6 minus 4 gives us positive 2. Negative 1 squared is 1. 5 squared is 25. 2 squared is 4. When we add those together, we get 30. So d is equal to square root of 30. That doesn't simplify, so we'll leave the square root of 30. Better to leave it as a simplified radical than to use a decimal. For our midpoint formula, again, we're just going to substitute the numbers for x, y, x1, x2, y1, y2, z1, z2 into our formula, and then simplify. So x1 is 2 plus x2 is 1. Y1 is negative 2 plus y2 is 3. Z1 is 4 plus z2 is 6. Well, 2 plus 1 is 3. 3 over 2 is 3 halves. Negative 2 plus 3 is 1 over 2 is 1 half. 4 plus 6 is 10, and 10 divided by 2 gives us 5. So the point 3 halves, comma 1 half, comma 5 is our midpoint. All right, next up, we're going to write the equation of a sphere with the center at 1, comma 5, comma negative 2, and a radius of 4. And then we're going to calculate the volume of the sphere. And the standard equation of a sphere with a center of h, comma k, comma j, and a radius r is x minus h quantity squared plus y minus k quantity squared plus z minus j quantity squared is equal to r squared. Notice this looks a lot like the equation of our circle, but with this extra term for the z coordinates. The volume of a sphere is given by v equals 4/3 pi r cubed. This is something that you saw in your geometry days. We're just giving you a little quick recap here. All right, so if we substitute our center coordinates and our radius into the equation of a sphere, we're going to put in 1 for h, 5 for k, and negative 2 for j. So x minus 1 squared plus y minus 5 quantity squared plus z minus negative 2 quantity squared is equal to 4 squared. X minus 1 squared, y minus 5 squared. When we subtract negative 2, that's adding 2, so we're going to get z plus 2 quantity squared, and 4 squared gives us 16. So here's our equation of our sphere. And then to find the volume, if we put 4 in for the radius in our volume formula, 4/3 times pi times 4 cubed is 256 pi over 3, or if you were to get that as a decimal, about 268.08. All right. This time, example 4, we're going to write the standard equation of the sphere and identify its center and radius. So the equation we're working with is x squared plus y squared plus z squared plus 4x minus 2y plus 8z plus 10 is equal to 0. Notice that we have 3 squared terms this time, so we get to complete the square 3 times. I know you were all just so excited, right? Okay, if we group our our x terms, group your y terms, group your z terms into each of their own sets of parentheses, and the number that doesn't have a variable is going to be kept on the outside of the parentheses. And now if we complete our squares, okay, half of 4 is 2, 2 squared is 4. There's no coefficient out in front here, so to balance out adding 4, we subtracted 4 here. For our y terms, half of negative 2 is negative 1. Negative 1 squared is positive 1. And to balance out that positive 1, we're going to subtract 1 out here. For our z terms, half of 8 is 4. 4 squared is 16. And to balance that out, we're subtracting 16 on the outside of the parentheses. And now if we do a little bit of simplifying, half of 4 is 2, so we get x plus 2 quantity squared. Half of negative 2 is negative 1, so y minus 1 quantity squared. Half of 8 is 4, so z plus 4 squared. And if we combine the 10 minus 4 minus 1 minus 16, we get negative 11. The last thing we're going to do to get this in standard form is to get our squared terms on one side, get the number term on the other side. So if we add 11 to both sides, the equation of our sphere in standard form is x plus 2 quantity squared plus y minus 1 quantity squared plus z plus 4 quantity squared is equal to 11. which means our center, the opposite of each of our numbers in our parentheses, is going to be -2, 1, -4. And since our equation is equal to r squared, if r squared is 11, then our radius is the square root of 11. Next up, the standard equation of an ellipsoid. Just a second, my computer's being slow here. Oh, there we go. An ellipsoid is a three-dimensional surface whose cross sections are either ellipses or circles, depending on which way you cut this shape. If we were to make cuts this way, kind of horizontally, I guess, we would get circles. If we were to be making cuts this way, we would be getting ellipses. Okay? An ellipsoid is symmetrical about three mutually perpendicular axes, which are called the principal axes, which intersect at the center. The standard equation of an ellipsoid with the center of h, k, j is x minus h squared over a squared plus y minus k quantity squared over b squared plus z minus j quantity squared over c squared is equal to 1. And notice this is just like our two-dimensional ellipse with the addition of this extra term for the z coordinates, where a, b, and c are the lengths of the semi-principal axes. With an ellipsoid, a, b, and c could be any length. There's not one that's guaranteed to be longer than the others, the way that we do with the ellipse. Okay? A is just the distance from the center to the side in the x direction. B is the distance from the center to the edge in the y direction. And C is the distance from the center to the edge in the z direction. The volume of an ellipsoid is given by v equals 4/3 pi times a times b times c. So instead of having r squared, r times r, we have the lengths of these semi-principal axes. All right, example 5, write the standard form equation for the ellipsoid, state the center and give the volume of the ellipsoid. And we're looking at the equation 9x squared plus 16y squared plus 36z squared minus 54x plus 360z plus 837 is equal to 0. Again, we're going to group our x terms, group our y terms, group our z terms. In this case, each of those square terms have a coefficient in front, so we're going to need to factor those out. So if you factor out 9 from your x terms, factor out 16 from the y term, and factor out 36 from the z terms, then we can complete our square. Half of -6 is -3. -3 squared is 9. But we didn't just add 9, we added 9 times 9. So to balance that out, we're subtracting 81 here. There is no y term. There's a y squared term, but there's no y term here. So if you really want to complete the square, half of 0 is 0, and 0 squared is 0. You can add 0 if it makes you feel better, but it's not necessary. For our z terms, half of 10 is 5, 5 squared is 25, but we didn't just add 25, we added 36 times 25, 900. So to balance that out, we're going to subtract 900 outside of the parentheses. And now if we do a little bit of simplifying, half of -6 is -3, so we have the x minus 3 quantity squared times our 9. We still have our 16y squared. For our z terms, half of 10 is 5. We get z plus 5 quantity squared times our 36. And when we combine all of our constant terms, 837 minus 81 minus 900, we get -144 equals 0. Our next step, we can add 144 to both sides to get this. And then our final step, because we want to get one side of this equation to equal 1, is to divide everything by 144. 9 goes into 144 16 times. 16 goes into 144 9 times. 36 goes into 144 4 times. And 144 divided by 144 is 1. So our standard equation for this ellipsoid is x minus 3 quantity squared over 16 plus y squared over 9 plus z plus 5 quantity squared over 4 is equal to 1. Our center is going to be the point 3, comma 0, comma negative 5, and opposite of what's in the parentheses. Our volume, using our formula, 4/3 pi times a times b times c. Well, we know a squared is 16, so a is 4. B squared is 9, so b is 3. If c squared is 4, then c is 2. And if we multiply 4/3 times pi times 4 times 3 times 2, we get 32 pi, or that's about 100.5. Your assignment, section 11.1 on WebAssign, or on page 783, 30, 31, 44, 48, 54, 57, and 58. Do note that question 54, there isn't an example exactly like it in the notes. However, in that particular problem, it gives you the endpoints of the diameter and asks you to come up with the equation of the sphere. So I want you to think about, if you know those endpoints, what formula would you use to find the center of the sphere? What formula would you use to find the length of the radius? Because once you know the center and you know the length of the radius, you can write the equation like we did in example 3. Please reach out if you have any questions. Good luck.